Now that we know how to complete the square, we can apply that process to better understand definiteness. So if we complete the square for a generic quadratic form, again, that means we represent the quadratic form with a real symmetric matrix, we find a spectral factorization, and write the quadratic form as lambda times our change of variable y1 squared plus lambda 2 times our change of variable y2 squared, and then we keep going until we get to our last eigenvalue multiplied by yn squared. The thing to point out here is that when we do this process, what we're doing is we're taking a linear combination of square terms. So if we care about the sign of the quadratic form, what we really care about are the signs of the eigenvalues here. So the eigenvalues of the symmetric matrix representing the quadratic form controls the definiteness of the quadratic form. Explicitly, what we're saying is that being positive definite is the same thing as saying that the eigenvalues are all positive numbers. Being positive semi-definite is the same thing as saying that the eigenvalues are all non-negative. Negative definite means the eigenvalues are all strictly negative. Negative semi-definite means that the eigenvalues are all non-positive. And indefinite means there is at least one positive eigenvalue and at least one negative eigenvalue. So if you know the eigenvalues of the symmetric matrix representing your quadratic form, you immediately know the definiteness of your quadratic form. And the reason you know your definiteness is because of the method of completing the square. So here's an example. Here we're looking at the quadratic form represented by this real symmetric matrix S. I bothered to find the eigenvalues, and I found that the eigenvalues of S here are -2, -1, and 0. What does that tell me? Well, the eigenvalues here are all non-positive. They're all not positive numbers. But I do have 0 on the list of eigenvalues, so they're not strictly negative. So this tells me that my quadratic form is negative semi-definite, but not negative definite. So if you know your eigenvalues, you know the definiteness of your quadratic form.